There is something in the universe that does not behave the way it should. It does not emit light. It does not reflect it, cannot be touched, photographed, or measured directly. And yet, wherever astronomers look, in every galaxy, in every corner of the observable universe, at every point in cosmic time, it is there, always there. Scientists have known about it for decades. They have named it. They have mapped it. They have built entire theoretical frameworks around what it must be doing, and why and how much of it exists. But here is what they will not say easily, in public, in press releases, in the carefully worded abstracts of peer-reviewed papers. They do not know what it is. Not really. They know what it does. They know how it behaves. They know it is responsible for holding galaxies together, for sculpting the large-scale structure of everything that exists, for making the universe look the way it does. But what it actually is, its nature, its origin, what it's made of, whether it is even matter at all in any sense we understand, that remains one of the deepest unsolved problems in all of science. And recently, several teams of astronomers independently noticed something new. Something that the existing models do not predict. Something that suggests this invisible presence. This thing that fills the universe, that surrounds every galaxy including our own, that dwarfs ordinary matter 5 to 1. May not be behaving the same way it used to. It may be changing, and no one can tell you why. Let's start at the beginning. Not the beginning of the universe, we'll get there, but the beginning of the mystery. It's 1933. A Swiss astronomer named Fritz Zwicky is studying the Coma Cluster, a massive collection of galaxies about 320 million light-years away. He's trying to measure the mass of the cluster, and he has two ways to do it. The first way is to count the galaxies, measure how bright they are, and use what we know about stars to estimate total mass. Standard physics. Clean mathematics. Done. The second way is to measure how fast the galaxies are moving around inside the cluster, their orbital velocities. In a gravitational system, the speed of an object's orbit is directly related to the mass holding it in. The more mass, the faster the orbit, in a predictable mathematical relationship that has worked reliably since Newton. Zwicky does both calculations. They don't match, not by a little, not by some small percentage that could be explained away by measurement error or approximation. They don't match by a factor of 400. The galaxies in the Coma Cluster are moving roughly 400 times faster than they should be, given the mass of all the visible matter Zwicky can account for. Which means one of two things. Either the physics is wrong, or there is something there that Zwicky cannot see. He calls it Dunkel Materie, dark matter. Most of his contemporaries ignore him. The measurement tools of 1933 are crude. Maybe he's wrong. Maybe there's a systematic error somewhere. Maybe the cluster isn't in gravitational equilibrium. There are a dozen ways to dismiss it, and for decades, most astronomers do. Then comes Vera Rubin. It is the 1970s. Vera Rubin is a staff astronomer at the Carnegie Institution in Washington, D.C. She has spent years fighting to be taken seriously in a field that does not easily welcome women, and she has found her niche in studying the rotation of galaxies. She focuses on spiral galaxies, galaxies like our own Milky Way, disc-shaped collections of hundreds of billions of stars rotating around a central core. The physics of how a spiral galaxy should rotate is well understood. Stars at the center, close to the massive concentration of matter there, should orbit quickly. Stars at the outer edges, far from the center, far from most of the mass, should orbit slowly. This is exactly what we see in our own solar system. Mercury races around the Sun in 88 days. Neptune takes 165 years. Distance from the mass center equals slower orbit. Basic Newtonian mechanics. Rubin measures the rotation curves of dozens of spiral galaxies. And what she finds is that they are all, without exception, wrong. The stars at the outer edges of these galaxies are not slowing down. They're moving at nearly the same speed as stars closer to the center. Some of them are moving faster than they should be at their distance. If you took away the central mass and let these outer stars move freely under the gravity of only what's visible, they would simply fly off into space. They should not be in orbit at all, but they are. Something is holding them, something with mass, something that does not emit or reflect light, something that extends far beyond the visible edge of the galaxy, forming an enormous invisible halo that wraps around every spiral galaxy we observe. Rubin publishes. This time, the field listens. Because this time, it's not one eccentric Swiss astronomer with limited data. This is systematic, repeated, independently verifiable evidence across galaxy after galaxy after galaxy. The universe contains something invisible, and there is a lot of it. How much exactly? This is where it gets staggering. When cosmologists today look at the full census of everything that exists in the observable universe, the breakdown is this: ordinary matter, the stuff made of protons, neutrons, electrons, the atoms that form everything you have ever seen or touched or thought about, every planet and star and gas cloud and human being and grain of sand, makes up approximately 5% of the total energy content of the universe. 5%. Dark matter makes up approximately 27%. And the remaining 68% is something else entirely: dark energy, the force driving the accelerating expansion of space itself, which we will come to later. But right now, focus on that number, 27%. Dark matter outweighs ordinary matter by more than 5 to 1. For every kilogram of stuff you can see and touch in the universe, there are more than 5 kilograms of something else, something invisible, something unknown. It is not a small correction. It is not a minor footnote in our understanding of reality. It is most of everything. By the 1990s and 2000s, the evidence for dark matter has compounded to the point where dismissal is no longer scientifically defensible. The rotation curves of galaxies, the velocities of galaxies within clusters, just like Zwicky measured, the gravitational lensing of background light around galaxy clusters, the way massive objects bend the path of light traveling behind them, revealing more mass than is visible, the large-scale structure of the universe itself, the cosmic web of filaments and voids that simulations can only reproduce correctly if dark matter is included. Every line of evidence points the same direction. And then comes the bullet cluster. In 2006, astronomers observed the aftermath of a collision between two massive galaxy clusters, a system called 1E0657-558, which has come to be known as the bullet cluster, because one of the subclusters has punched through the other and emerged on the far side, trailing a bullet-shaped wake of hot gas. They map it carefully. They look at where the hot gas is, gas that was stripped away from the galaxies during the collision and now forms a massive cloud between the two clusters, glowing in X-ray light. They look at where the actual galaxies are, far ahead of the gas on both sides, having passed through each other without much interaction. And then they map the gravitational lensing. They look at where the mass is according to the bending of light from background galaxies. The mass is not with the gas. The gas, which makes up the overwhelming majority of ordinary matter in these clusters, got slowed down by the collision, by electromagnetic interactions between all those charged particles slamming into each other. It piled up in the middle, but the mass, most of it, kept moving. It moved with the galaxies right through the collision without slowing down, without interacting, because dark matter doesn't interact electromagnetically. It only interacts gravitationally, passed through itself, through the gas, through everything, like two ghosts walking through each other. The bullet cluster is, for most cosmologists, the single most direct observational evidence for dark matter ever obtained. You can see the mass separated from the ordinary matter. You can see it behave exactly as dark matter theory predicts. It is breathtaking, and it still tells us nothing about what dark matter actually is. Here is where the real strangeness begins, because despite all this evidence, despite more than 90 years since Zwicky's first hint, despite decades of increasingly precise cosmological measurements, despite the most sensitive particle detectors ever built, placed deep underground to shield them from interference, we have never directly detected a single dark matter particle. Not one. Every experiment designed to catch dark matter interacting with ordinary matter has come up empty. Let's talk about what they've tried. The leading candidates for dark matter for a long time were called WIMPs, weakly interacting massive particles. The name tells you what they are: particles with significant mass like a heavy proton, but that interact with ordinary matter only through the weak nuclear force and gravity, not through electromagnetism. This would make them nearly invisible. They wouldn't emit or absorb light, but very occasionally, rarely, they might collide with an ordinary atomic nucleus and deposit a tiny amount of energy. That tiny deposit of energy is what the experiments look for. So you build a detector. You take something very dense and pure, maybe xenon, maybe germanium, and you put it deep underground, a kilometer down, so the rock above you absorbs all the ordinary cosmic radiation that would create false signals. You cool it to temperatures close to absolute zero, because thermal noise would drown out the signal you're looking for. You shield it from everything. You run it for years, and then you wait, and you wait, and you wait. The LUX detector in the Homestake mine in South Dakota. Then LUX Zeppelin, its far more sensitive successor. The Xenon 1T experiment, and then XENONNT in the Gran Sasso laboratory in Italy. Panda-X in China. The results from all of them are, in a sense, remarkable because they have measured essentially nothing. They have ruled out enormous swaths of parameter space. They have determined that if WIMPs exist, they either interact far more weakly than expected, or their mass is outside the ranges these experiments are sensitive to. Which means either WIMPs are not dark matter, or they are hiding so perfectly that even our most sensitive instruments cannot catch them. So maybe it's axions instead. Axions are a different candidate, much lighter than WIMPs, originally proposed in the 1970s to solve an unrelated problem in particle physics called the strong CP problem. They would be extraordinarily light, with masses perhaps a billion times less than an electron. They would be produced in enormous quantities by the hot plasma of the early universe and would naturally form a cold, slowly moving sea of particles, exactly the kind of thing that could serve as dark matter. They would also, in the presence of a strong magnetic field, very occasionally convert into a photon of microwave light. A single, barely detectable photon. Experiments like ADMX, the Axion Dark Matter experiment in Seattle, have been searching for exactly that signal for years, threading microwave cavities through powerful magnetic fields, listening for the whisper of an axion converting. Nothing confirmed yet. Maybe it's primordial black holes formed in the dense, violent conditions of the early universe, before any stars existed. These would be purely gravitational objects, made of ordinary matter compressed beyond any possibility of interaction. They would fit naturally into the universe, cluster in halos around galaxies, and interact with nothing. But observations of gravitational lensing, particularly microlensing surveys watching for black holes passing in front of distant stars and magnifying their light, have placed strong constraints on this possibility. Primordial black holes at certain mass ranges have been largely ruled out as the primary component of dark matter. Some ranges remain open, but they'd have to be very specifically sized, and even then, the explanation feels incomplete. Maybe dark matter isn't a particle at all. Some physicists have proposed modifications to the laws of gravity themselves. If gravity behaves slightly differently at the low accelerations found in the outskirts of galaxies, you might not need dark matter to explain the rotation curves. These theories, collectively called modified Newtonian dynamics, or MOND, and its relativistic extensions, have had some successes in predicting galaxy rotation and some spectacular failures when applied to galaxy clusters and the cosmic large-scale structure. The bullet cluster is particularly damaging to these theories. The separation of mass from ordinary matter in that collision is very hard to explain if there is no actual dark matter there. Most physicists regard MOND as an incomplete description of something, perhaps a clue toward a deeper theory, rather than a replacement for dark matter. And then there is the newest and strangest category, ultralight dark matter, sometimes called fuzzy dark matter. The idea here is that dark matter is made of particles so extraordinarily light, perhaps 10 to the negative 22 times the mass of a proton, that quantum mechanical effects become important on cosmic scales. Each particle would have a de Broglie wavelength thousands of light years across. The dark matter wouldn't behave like a sea of individual particles at all. It would behave like a quantum wave, forming smooth, coherent structures with quantum interference patterns in the density of dark matter halos. This model has some interesting predictions. It would suppress the formation of very small dark matter structures. Tiny dwarf galaxies that current dark matter models predict should exist in enormous numbers around large galaxies like ours, but that observations have never quite found enough of. It might explain the apparent absence of dark matter in the very centers of galaxies, where standard models predict dense spikes but observations often find flat, smooth cores. It also makes dark matter even more bizarre, even less like anything we have ever encountered, even further from any intuitive understanding. And it still hasn't been confirmed. The honest summary of where we stand is this: we know something is there. We know it's most of the universe. We know it shapes everything we see, and we do not know what it is. Every candidate has problems. Every detection claim has either failed replication or been explained away. Every experiment designed to find it has found nothing. This is not a small gap in our knowledge. This is a fundamental, profound, unsettling hole at the center of our best understanding of reality. But here is what makes dark matter so strange, so central, so impossible to simply dismiss even when every detection effort fails. Without it, none of this exists. Not the galaxies, not the stars, not us. Let me explain. Go back to the very beginning. The universe is 380,000 years old. Still an infant. Ordinary matter is a hot plasma of protons and electrons, locked together by radiation, unable to collapse. The universe is smooth, almost perfectly uniform, with density variations of only about 1 part in 100,000. Those tiny variations, quantum fluctuations from the first instance of existence, stretched to cosmic scales by inflation, are the seeds of everything. But ordinary matter alone cannot grow them fast enough. Radiation pressure fights against gravity. Every time ordinary matter tries to fall into a denser region and collapse, the pressure from photons pushes it back out. The fluctuations oscillate, creating the patterns we see in the cosmic microwave background, but they don't grow. Dark matter is different. It doesn't interact with radiation. It doesn't feel that pressure. It can begin collapsing into denser regions right away, even while the ordinary matter is still locked in the plasma. So it does. Over hundreds of millions of years, dark matter collapses into filaments and sheets and knots, forming the scaffold of the cosmic web. And when, at about 380,000 years, the universe finally cools enough for electrons to combine with protons into neutral hydrogen, the moment called recombination, ordinary matter is suddenly free from radiation pressure. And it falls immediately into the gravitational wells that dark matter has already prepared. That is how galaxies form. Ordinary matter falling into dark matter halos. Ordinary matter compressing and heating and igniting as stars. The cosmic web, the vast filamentary structure of galaxy clusters and voids that spans the observable universe, is the fossil of dark matter's early gravitational architecture. Every galaxy is, in this sense, a luminous decoration on an invisible dark matter skeleton. Zoom in now to the scale of individual galaxies. Dark matter halos extend far beyond the visible disk of a galaxy. The Milky Way's dark matter halo is estimated to extend roughly 600,000 light-years in radius. The visible disk of stars and gas is only about 100,000 light-years across. The dark matter halo dwarfs the galaxy we actually live in, and it's not uniformly distributed. Within the halo, dark matter has structure. Dense clumps orbit the central galaxy. We call them subhalos. Some of these subhalos have enough ordinary matter in them to form small dwarf galaxies, which is why our Milky Way is surrounded by a collection of small satellite galaxies like the Large and Small Magellanic Clouds and dozens of fainter ones. Others have no ordinary matter at all. They are purely dark matter clumps without a single star. Ghost satellites orbiting our galaxy invisibly. How many? Simulations suggest there should be thousands, maybe tens of thousands. We have found only a few dozen actual dwarf galaxies around the Milky Way. This is called the missing satellites problem, and it is one of several small-scale anomalies that suggest either our dark matter models need refinement, or there are processes stripping ordinary matter from small dark matter subhalos, or something else is going on that we don't understand. Let's go even larger, to the cosmic web itself. If you could step outside the universe and look at it from a vast distance, you would not see a uniform fog of galaxies. You would see a web, a vast, three-dimensional structure of filaments, dense strings of matter hundreds of millions of light-years long, intersecting at nodes where massive galaxy clusters sit. Between the filaments, voids, enormous, nearly empty expanses of space hundreds of millions of light-years across. This structure, this cosmic web, is one of the most beautiful and strange things science has ever revealed. And it exists entirely because of dark matter. Computer simulations of the universe, run from initial conditions matching what we observe in the early universe, produce something that looks strikingly like what we see, but only when dark matter is included. Without dark matter, the simulations produce a smooth, structureless universe. Nothing like what we actually see. The cosmic web doesn't form. Galaxies don't exist. With dark matter, everything clicks. Filaments form. Clusters grow at intersections. Voids expand. The large-scale structure of the universe that took billions of years to form emerges naturally from the mathematics of dark matter gravity. This is perhaps the strongest argument for dark matter's existence. Not any single measurement, but the fact that it makes the entire observable universe make sense. Now here is where things begin to change, because the universe is not static. It has not always looked the way it looks now, and astronomers in recent years have been able to look backward in time, really backward to when the universe was only a fraction of its current age, and compare the dark matter distribution then to now. And something is different, not enormously, not dramatically, but the models don't quite fit anymore. There is a problem in cosmology that has been building for about a decade. Scientists call it simply the tension, or more precisely several tensions, because there are multiple places where different measurements of the universe, made by different methods, using different instruments, studying different things, do not agree with each other. They disagree in ways that are too systematic to be explained by measurement error alone. They disagree in ways that all seem to point in a consistent direction, in ways that suggest, taken together, that something in our model of the universe is wrong, or that something in the universe itself is not behaving the way it should. The most famous of these is the Hubble tension. The Hubble constant is the rate at which the universe is currently expanding. It has units of kilometers per second per megaparsec for every megaparsec of distance between 2 points in space. A megaparsec is about 3.26 million light-years. Those points are moving apart at a rate of about 70 kilometers per second. You can measure the Hubble constant two ways. The first is what cosmologists call the early universe method. You look at the cosmic microwave background, the afterglow of the Big Bang, the most precisely measured thing in all of cosmology, and you fit the standard cosmological model to its patterns. You extrapolate forward in time to predict what the expansion rate should be today. The second is the local method. You measure the distances and recession velocities of galaxies and objects near enough to observe directly. You build a cosmic distance ladder using Cepheid variable stars, type Ia supernovae, and other standard candles, and you measure the expansion rate directly here, now, in the present universe. Both methods are extraordinarily precise. Both have been refined and improved for decades. Both have had their systematic errors checked and rechecked. And they disagree. The early universe method gives a Hubble constant of about 67 to 68 kilometers per second per megaparsec. The local method gives a value of about 73 to 74. That difference, 5 to 6 kilometers per second per megaparsec, sounds small. But statistically, given the precision of these measurements, the probability that this disagreement is due to chance is now estimated at roughly 1 in a million or smaller. This is not a rounding error. This is a real discrepancy. Something is wrong. There are several possible explanations. One is that there are systematic errors in the measurements, subtle biases in how we calibrate standard candles, or in how we interpret the cosmic microwave background that skew the results in consistent ways. Enormous effort has gone into finding these errors. They have not been found. Another is that the standard cosmological model is incomplete. That dark energy, the 68% of the universe's energy budget that drives the accelerating expansion, doesn't behave exactly as our simplest models assume. That it varies over time, that it was slightly different in the early universe than it is now. And this is where dark matter re-enters the story. Because if dark energy is different than we think, if it evolves, if it interacts with other things, if it has properties we haven't accounted for, then the dark matter distribution in the universe might also look different than our models predict. And recently, it does. In 2023 and 2024, the Dark Energy Survey, a massive photometric survey covering a significant fraction of the southern sky, released results from its analysis of weak gravitational lensing. Weak lensing is the subtle distortion of background galaxy shapes caused by the gravitational influence of all the mass between us and them, dark matter included. By carefully measuring those distortions across millions of galaxy images, you can map the distribution of matter in the universe and, crucially, how clumped it is, how much mass is concentrated in dense structures versus spread smoothly in voids. The parameter that measures this clumpiness is called S8. The Dark Energy Survey measured S8. The cosmic microwave background, processed through the standard cosmological model, predicts S8. They disagree. The universe, at the scales the survey examined, appears smoother than our model predicts it should be. The dark matter distribution is less clumped. Something has been working over the history of the universe to smooth things out slightly more than the standard model expects. This is the S8 tension, and it is deepened by independent results from the kilodegree survey, another weak lensing analysis. Both get similar answers. Both disagree with the standard model in the same direction. Now add one more layer. In 2023, the Dark Energy Spectroscopic Instrument DESI began releasing results from the most precise map of the three-dimensional distribution of galaxies ever made. DESI observes baryon acoustic oscillations, a pattern embedded in the distribution of galaxies by sound waves in the early universe. These oscillations act as a standard ruler, allowing precise measurement of cosmic distances at different epochs of the universe's history. By comparing how those distances change across cosmic time, DESI can probe dark energy's behavior across billions of years. The first results, released in 2024, showed something unexpected. When the DESI data were fit with a model in which dark energy is allowed to change over time, rather than being fixed at a constant value, the fit was significantly better. Dark energy, the results suggested, may have been stronger in the past and is weakening now. Or it may oscillate. Or it may have some other time-varying behavior. This is not confirmed. One dataset is not enough. But when DESI's results were combined with other independent datasets, supernova surveys, cosmic microwave background measurements, the preference for evolving dark energy became more significant. Not at the level of a discovery claim, but enough to take seriously. And if dark energy is evolving, if the force driving cosmic expansion is different today than it was 5 billion years ago or 10 billion years ago, then everything our models predict about the growth of structure, the clustering of dark matter, the formation of galaxy clusters needs to be reconsidered. The universe may be something slightly different from what we thought it was. Let's come back to the strangeness. There is something almost eerie about the situation we find ourselves in. We live inside a structure, this galaxy, this solar system, this planet, that exists only because dark matter built it. We are the product of processes that require dark matter halos to form first, to create the gravitational wells that ordinary matter fell into, to spark the gas clouds that became the stars that forged the atoms that make us. We owe our existence to something we cannot see, cannot touch, and cannot identify. And now, as we build the tools precise enough to actually test our models of this invisible architecture in detail, and as we look more carefully at more cosmic epochs with more data, the architecture doesn't quite look the way we thought it would. Something is different, and we do not know what. Here is one possibility that some physicists find uncomfortable enough to avoid discussing but intriguing enough to not dismiss. Dark matter may interact with itself. In the simplest models, dark matter particles interact with each other only through gravity. But gravity is the weakest force. If dark matter has its own forces, a dark electromagnetism, a dark nuclear force, some interaction that operates only between dark matter particles and not with ordinary matter, then dark matter wouldn't just be a cloud of non-interacting particles. It would have its own physics. This is called self-interacting dark matter, and it has some attractive properties. Self-interacting dark matter would behave differently in dense environments, like the centers of galaxies or inside massive galaxy clusters. The collisions between dark matter particles would redistribute energy and angular momentum, smoothing out dense central spikes into flatter cores. This would help explain why observed galaxy rotation curves often show flat central cores rather than the sharp peaks that simpler dark matter models predict. It would also change the behavior of dark matter in cluster collisions. In the bullet cluster, the dark matter passed through itself without slowing down significantly, which constrains how strong the self-interaction can be. But in other clusters, there are hints of offset between the mass center and the galaxy center, a hint that dark matter might have slowed down just slightly. Not enough to rule out self-interaction, but enough to keep it interesting. If dark matter interacts with itself, if it has its own rich physics that we are completely blind to, then the dark universe is not a featureless sea of passive particles. It has its own structure, its own dynamics, its own history. There could be dark atoms, dark chemistry, dark stars, entire dark matter structures that formed alongside our own universe, that permeate the same space, that overlap with everything we know but never interact directly. We would have no way to know. The universe we can see might be a thin, luminous film on the surface of something far more elaborate. And then there is what some physicists call the coincidence problem. Dark matter makes up 27% of the universe's energy. Ordinary matter makes up 5%. Dark energy makes up 68%. These numbers are very specific. Why these values? Why not 99% dark energy and 1% everything else? Why not equal amounts of dark matter and ordinary matter? The dark energy coincidence is particularly striking. Dark energy density is constant. It doesn't dilute as the universe expands. Matter density does dilute. As the universe grows, the same amount of matter fills a larger volume, so the density drops. In the early universe, matter dominated. In the far future, dark energy will completely dominate, and matter will be negligible. But we live right now in this specific epoch, when dark energy and matter are within an order of magnitude of each other, within a factor of 10. In cosmic history, this window is very narrow. Why do we exist at this particular moment? One answer is anthropic selection. You can only ask this question in an epoch where matter density is high enough for stars and planets and people to form, which constrains when the question can be asked. But another answer is, maybe these ratios are not coincidences. Maybe there are connections between dark matter and dark energy that we don't understand. Maybe they are aspects of the same underlying field or substance, with properties that naturally produce these values. We don't know. In the last 2 years, the observational landscape has changed dramatically. The James Webb Space Telescope has been peering into the early universe with a precision and sensitivity no instrument before it could match. And what it has found has surprised nearly everyone. In the first year of observations, Webb found galaxies, fully formed, massive, luminous galaxies, at redshifts corresponding to when the universe was only 300 to 500 million years old. Galaxies that, according to our standard cosmological model, should not yet exist. The universe wasn't old enough, according to our calculations, to have assembled that much mass into that many stars in that short a time. Some of these galaxies contain as many stars as the Milky Way. Some of them appear to contain supermassive black holes already, in a universe that is, at those epochs, only 2 to 4% of its current age. The standard model of structure formation, which depends critically on dark matter's behavior, does not easily produce these galaxies. Not at those sizes, not at those redshifts, not in that abundance. There are possible explanations. Maybe these galaxies are brighter than they appear massive. Maybe star formation in the early universe was more efficient, creating more light per unit of mass, which makes galaxies look more massive than they are. Maybe there are processes we haven't fully modeled, feedback from supernovae, or from the first generation of massive black holes, that concentrate star formation in unexpected ways. Maybe our calibration of how we convert observed light to stellar mass is systematically off in the early universe. Or maybe, and this is the explanation that makes theorists nervous, the dark matter model needs revision. Maybe dark matter was distributed differently in the early universe than standard models predict. Maybe it clumped faster or in different configurations, allowing galaxies to form earlier. None of these are ruled out. All of them are actively being investigated. What's clear is that the early universe is not quite what we expected, and Webb keeps finding things that push on the edges of our understanding. In 2024, Webb observed a galaxy cluster at a redshift of approximately 4.9, meaning we're seeing it when the universe was about 1.2 billion years old. Fully formed massive galaxy clusters, the largest gravitationally bound structures in the universe, should not exist that early. They take time to assemble. Dark matter halos need to merge and grow. The standard model says you shouldn't have massive clusters that early, but there it is. Meanwhile, the Euclid Space Telescope, launched in 2023 specifically to map the dark universe, to measure the distribution of dark matter through gravitational lensing across billions of light years and billions of years of cosmic time, has begun releasing its first results. Euclid's mission is precisely to test whether dark matter and dark energy behave the way we think they do across cosmic time, to map the cosmic web in 3 dimensions, to measure the growth of structure, the clumping of dark matter at different epochs and compare it to model predictions. Its first data releases have confirmed the quality of the instrument, the precision of the lensing measurements. The science results that will actually test the models are still coming. But what astronomers are watching for in the coming years of Euclid data is whether the S8 tension gets worse, whether the universe is even smoother, even less clumped than the standard model predicts, whether the dark matter distribution at earlier epochs shows the anomalies that more recent surveys hint at. If it does, if the tension grows, then the standard model will need to change. Let's talk about what change might look like. One option is a revision to dark matter itself, some new property, some new interaction that changes how dark matter clusters. Self-interaction, as we discussed, or a coupling between dark matter and dark energy, a dark sector, where these 2 mysterious components exchange energy in a way that affects both the expansion history and the growth of structure. Such models have been explored. Some of them relieve the Hubble tension. Some of them relieve the S8 tension. None of them yet do both simultaneously in a completely satisfying way. But the direction of travel in theoretical cosmology is increasingly toward richer, more complex dark sectors. A hidden universe parallel to ours, following its own rules, shaping ours from the outside. Another option is a revision to gravity itself, not MOND, which has the problems we discussed, but something more subtle. Some theories propose that general relativity, our best theory of gravity and the framework on which all of cosmology is built, might need modification on the largest cosmological scales. Maybe gravity behaves slightly differently when distances are measured in billions of light years rather than millions. Maybe the equations need a small correction term that becomes important only on the scale of the observable universe. These modifications could, in principle, change how structure grows over cosmic time, potentially smoothing things out in ways that match the observations. The problem is that general relativity has passed every test we've thrown at it, at every scale we've managed to probe. It is extraordinarily well confirmed. Modifying it is not done lightly, but if the data continue to tension the standard model, lightly won't be an option for much longer. Let me step back from the data for a moment, because I want to talk about what it means to live in a universe that is mostly made of something you cannot perceive. Most of what exists in the observable universe, most of the mass, most of the large-scale structure, the scaffolding that holds everything together, is invisible to every instrument we have built, every photon we have ever captured, every particle we have ever detected. You are not immersed in empty space. You are immersed in dark matter. Right now, wherever you are reading this, thousands of dark matter particles are passing through your body every second. Through the walls, through the earth, through the air. They pass through everything because they interact with ordinary matter only through gravity, and gravity at the scale of a human body is utterly negligible. They don't know you're there, and you don't know they're there. You live inside something vast and invisible and fundamental, and it passes through you without a trace, and it always has, and it always will, for as long as you exist. And this is not metaphor. This is the actual, literal physical situation you are in. There is a concept in physics and philosophy called the view from nowhere, the idea of describing reality from a perspective outside any particular observer, from a neutral standpoint that shows things as they are independent of any point of view. The universe does not have a view from nowhere. It has observers embedded within it, limited to their local perspective, studying the universe from inside using instruments made of the 5% of the universe they can interact with. We are made of ordinary matter. We see with photons. We detect with detectors built from atoms. And from this very specific, limited vantage point, we are trying to understand a universe that is 85 to 95% stuff we cannot directly perceive. It is as if you were born inside a small illuminated room, inside a vast dark building, and you are trying to understand the architecture of the building from the patterns of sound you hear through the walls, the slight trembling of your floor from the movements of things outside, the occasional distortion of light that seems to come from nowhere. You are building a picture of the dark, from clues, from shadows, from the shape of absence. And it's working. That's the extraordinary thing. Our models, as imperfect as they are proving to be at the edges, have produced a description of the universe that matches the vast bulk of what we observe with stunning precision. The cosmic microwave background, the abundances of light elements, the large-scale structure, the existence of galaxies and clusters and voids, all of it predicted and confirmed. And now, at the edges, the model is straining. The tensions are real. The anomalies are accumulating. Something is not quite right. And that is not cause for despair. It is cause for excitement, because every time the edges of a model start to fray, it means that a deeper truth is hiding just beyond what we've been able to see. It means the map is about to expand. So where does this go? What happens next? What are we going to learn in the next 10 to 20 years about the dark universe? Let me walk you through what's coming. The Vera Rubin Observatory in Chile, named appropriately for the astronomer who did so much to establish dark matter's existence, is coming online now. It will survey the entire southern sky every few nights for 10 years, creating the most comprehensive movie of the universe ever made. Every transient event, every variable star, every moving object in our solar system, every supernova, all of it cataloged in real time. But its deepest scientific contribution will be in weak gravitational lensing. By accumulating billions of galaxy images over 10 years, the Rubin Observatory will measure the dark matter distribution with a precision that dwarfs anything that came before. If the S8 tension is real, if the universe is genuinely smoother than standard models predict, Rubin will see it clearly, definitively. If it confirms the tension, the standard model will need to change. Probably significantly. If it resolves the tension, if better calibration and more data bring everything into agreement, then we breathe a collective sigh of relief and continue refining our existing framework. Either outcome would be profound. On the particle physics front, the search for direct detection of dark matter is entering a new phase. The next generation of xenon detectors, experiments like XLZD, a proposed successor to LUX Zeppelin and XENONNT, with a detector mass of 50 to 100 tons, will push sensitivity to levels where they can detect the irreducible background noise from solar neutrinos. This is called the neutrino floor, a background signal from ordinary neutrinos that mimics what a WIMP signal would look like, and below which distinguishing dark matter from neutrinos becomes extremely difficult. If WIMPs exist within the parameter space these experiments can probe, they will be found. If the experiments reach the neutrino floor and still find nothing, the WIMP hypothesis, at least in its simplest form, will be effectively ruled out. That would be a major moment. Ruling out the leading candidate forces a rethink. It would push theorists toward axions, toward self-interacting dark matter, toward more exotic possibilities. The axion searches are also scaling up. Experiments are now being proposed that could scan the full range of masses where axions are most theoretically motivated. If dark matter is made of axions, the next decade of experiments has a real chance of finding them. Perhaps the most exciting near-term prospect is gravitational wave astronomy. Since 2015, LIGO and its partner detectors have been listening to the universe in gravitational waves, ripples in the fabric of spacetime produced by colliding black holes and neutron stars. This has opened an entirely new window on the universe, allowing us to observe objects and events that emit no light at all. If primordial black holes form a significant fraction of dark matter, some of them should be merging, and those mergers should produce gravitational wave signals with characteristic properties. The mass distribution of the merging objects, the rate at which mergers occur, the way the signals cluster, all of this could, in principle, reveal a population of primordial black holes that matches the dark matter abundance. The proposed Einstein telescope in Europe and the Cosmic Explorer in the United States, third-generation gravitational wave detectors of unprecedented sensitivity, would be able to detect mergers far smaller and farther away than current instruments. They might see a stochastic background of gravitational waves from all the primordial black hole mergers across the observable universe, like a hiss of static beneath the discrete events. If that background looks right, if it has the properties that primordial black hole dark matter would produce, it would be a discovery of the first magnitude. And then there is the longer-term prospect of direct detection through entirely different means. Some theorists have proposed that if dark matter self-interacts strongly enough, it could form dense compact objects, dark stars, dark blobs, inside ordinary matter halos. These could, in principle, be detected not through their light or their particle interactions, but through their gravitational influence on nearby ordinary stars. Subtle perturbations in stellar orbits, slight accelerations that can't be explained by visible mass. This is extraordinarily difficult to detect, but space astrometry missions, the current Gaia spacecraft, and its proposed successors, are measuring stellar positions and motions with precision measured in microarcseconds. Precision good enough, in principle, to detect the gravitational influence of compact dark matter objects if they exist in the right density. We are not there yet, but we are approaching a level of measurement precision where the universe can no longer easily hide things from us. The universe is very old, 13.8 billion years old from the Big Bang to the present moment. For 13.5 billion of those years, no one was watching. No one could have been. For most of cosmic history, the universe existed without observers, without consciousness, without curiosity, without anyone to notice that it was there at all. Dark matter was building its web long before any star ignited, long before any planet formed, long before any molecule arranged itself into something that could replicate and evolve and eventually look up at the sky and wonder. And in that long dark time, the first billion years, the first 5 billion, the long slow climb of cosmic structure toward complexity, the dark matter halos grew and merged, the filaments thickened, the voids deepened. The universe arranged itself, patiently, in the dark, into the architecture that would eventually allow life. Not for the sake of life, not intentionally, because gravity is gravity and matter falls into wells and mathematics is mathematics. But the result is, here we are, made of 5%, surrounded by 95% we cannot see. Alive in a tiny illuminated pocket of an overwhelmingly dark cosmos, asking what the dark is made of. There is something deeply right about not knowing. I don't mean that ignorance is good, or that we should stop trying to understand. The work of science, the careful, cumulative, relentless effort to build better models, to design better experiments, to look more carefully at what the universe is actually doing, is one of the most meaningful things our species has ever undertaken. But the fact of not knowing, the fact that we can be this far, this sophisticated, this technically advanced, and still have 85% of the universe be, in some fundamental sense, a mystery. That fact is humbling in a way that's worth sitting with. We are very new. The universe is very old. We have been asking questions seriously, rigorously, with mathematics and instruments and peer review for maybe 500 years. In a universe 13.8 billion years old, 500 years is nothing. It is less than nothing on cosmological timescales. We are infants who have opened our eyes and started to look around, and we are surprised at how much we can't see yet. Of course, there is dark matter. Of course, there is dark energy. Of course, the universe has components we've only just noticed in the last century. We would be very strange beings if we had figured everything out already. The mystery is appropriate. The mystery is where we should be at this stage. The night sky looks the same tonight as it did before anyone knew about dark matter. The stars are the same. The galaxies, visible with binoculars in the dark patches between constellations, are the same fuzzy smears of ancient light they've always been. But you know something now that no human knew before 1933. You know that inside each of those smears, invisible dark matter halos extend far beyond the visible stars. You know that the filaments of the cosmic web, dark threads hundreds of millions of light years long, run between the galaxies and clusters in patterns that span the universe. You know that the space between stars is not empty. Not quite. It is filled with dark matter moving slowly at the speeds of orbiting galaxies. Invisible particles streaming through the light years, passing through everything, including you. You are, right now, passing through a river of dark matter. It passes through you and continues on its trajectory, indifferent, silent, as it always has been. The dark universe holds you without knowing you're here. We are, possibly, at a turning point. The tensions in the Standard Model, the Hubble tension, the S8 tension, the early galaxy problem may resolve. New data may show systematic errors in the old data. Better models may absorb the anomalies without fundamentally changing the picture. Or they may not. The DESI results on dark energy. The Rubin Observatory's weak lensing survey. The next generation of dark matter detectors. The gravitational wave observatories. The continued discoveries of Webb, staring back toward the first billion years of the universe and finding things that weren't supposed to be there yet. All of it is coming. All of it will sharpen the picture. And there is a non-trivial chance, not a certainty, not even a strong probability, but a real chance, that in the next 10 to 20 years, we will look back at this moment as the beginning of the revision. The moment when enough anomalies had accumulated that something had to give. When the next big idea was just about to arrive. We don't know what that idea will be. By definition, we can't. If we could describe it now, it would already be here. But the universe is patient. It has been waiting for us to ask the right questions for 13.8 billion years. Can wait a little longer. And tonight, the dark matter streams through you, and the galaxies hold their shape in the invisible halos that surround them, and the cosmic web stretches in the dark between the stars, and the universe expands into nothing, carrying everything with it, and no one knows quite what it's made of, and somewhere in the data, hidden in the measurements and the tension models and the anomalous redshifts, the answer is probably already there, waiting to be found. Sleep well.